Hey students, today we're going to wrap up power functions, which you started last week. You should have your blue packet already finished, and then from here we're just going to be working on practicing looking at power functions and thinking about what those graphs are going to look like. Goal is to discuss concavity here, then it's going to be practicing graphing. Then you're going to discuss some inverse and direct variation, and then you'll have homework which you should have time to start in class. First thing I want you to do is with your packet in front of you, you guys are going to find the average rate of change on this first graph over 4 intervals. Find the average rate of change on the interval of 0 to 1, on the interval of 1 to 2, 2 to 3, and 3 to 4. So basically, if I am to take a pen and and I draw this line here, you are basically finding the slope of the straight line that connects the endpoints over those intervals. So go ahead and find the average rate of change on both of these graphs, and then pause the video, do the work, and then turn the video back on. All right, right now you should have already done the work, and here are the answers that I came up with. So I looked at the average rate of change over these intervals, and I found that it's 1. Here the average rate of change is 3, 5, and 7. And whether you did y2 minus y1 over x2 minus x1, or you actually just counted it, it doesn't really matter. But here's the work down below that you guys can see. And let me move this. And hopefully what you're seeing is that the average rate of change from 1 to 3 to 5 to 7 as we moved from left to right on the graph. Or on this graph over here, as we come down, it went from -7 to -5 to -3 to -1. And in both of these cases, the average rates of change are increasing over intervals as you move from left to right. And because the average rate of change are increasing, that is why both of these functions are concave up. Okay, here are 2 more functions. Find the average rates of change on the interval of 0 to 1, 1 to 4, and 4 to 9. And then over here on the intervals of 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Pause the video to do your work and then come back. All right, you should have found the average rates of change on those intervals. And you should see that the average rate of change here went from 1 to 1/3 to 1/5. And then over here you should see it went from -1, -3, -5, and -7. Here's the work, and hopefully you're seeing that over increasing intervals the average rate of change is decreasing. Same thing over here. And because both of the average rates of change are decreasing, that is why both of these functions that are curving down like that are concave down. All right. Now what I want you to do is I want you to work on the graphs, and I think that there are 10 of them if I'm looking. Oops, those are the answers. I think there are 10 of them. And go ahead and do all those, pause the video, think about each one, thinking about the work you did on your packet, and then come back and we'll talk about it. All right. So these should be done, the 1 through 10, and here are the answers to them. So on this one here, you should see it's just a square root function with a leading coefficient of 3, which just vertically stretched it up. It is only in the first quadrant because you can only take an even root of positive input values on your x-axis, so it's only here. This one, we'll see if I can kind of graph as I go. I start to think about where would x to the 1/3 be, and x to the 1/3 would just look like this. And then I think about what this -4 does in front, and it flips it over the x-axis, and it also then vertically stretches it up. So hopefully you're able to see here that it is starting off in quadrants 1 and 3, and then over here it's ending up in quadrants 2 and 4. Here's these functions. This one's a hard one. Let's see if I can explain it. I would look at what x to the 2/3 looks like. Knowing that we just saw x to the 1/3, and here's x to the 2/3. X to the 1/3 is like this. But what happens when you square numbers is they become positive. So right here, it makes all these negative values go to right here. So stop and think about that and replay it if you need. X to the 1/3 would have been, oops, if I can graph it all along this red line. And then when you get to the 2/3, it squares those numbers so that you're getting this function right there. And the negative in front reflects it over. Here's what 2 times x to the 3/4 power is. Notice that when this power is even, which is the only quadrant it's ending up in? Maybe you need to take some notes on the side of your paper, like, hey, if the denominator or your root is even, you're only getting answers in quadrant 1. Here are the answers to the others. Pay attention now that, hey, this exponent is bigger than 1. What happened to this concavity? And if you think about it, what is y equals x to just the first power? That is literally a straight line on basically a 45-degree angle. So it's when that exponent goes above 1, it becomes concave up, and when this exponent up here is below 1, it becomes concave down in that quadrant. I'll let you continue looking at some of these, and then we can go over and discuss more of them in class. You can grade all your work. So here's 7 and 8. Look what's happened when you have those negative exponents. It really means x is in the denominator, so you get those vertical asymptotes happening there. And then here's some more to think about. Why is this only in the first quadrant? Why is this one in quadrants 3 and 4? So things to think about, and then come back to class the next day, and we can talk about any of the ones you're still having questions on. From here, you can pause the video and take some notes on direct variation. Direct variation is basically saying that as x goes up, y goes up. And direct variation problems are just kind of applications of power functions. So you can pause and take notes. All right, inverse variation are more applications of power functions, and basically here, if you look at it this way, it's basically saying what inverse variation is as x goes up, y goes down, and vice versa. An example that I used in class of the inverse variation is that in the problem solving, when we had 1 test, they were all worth 10%. When you had 2 tests taken for problem solving, they're each worth 5%. When you had 3 tests, they were 3 1/3. So hopefully you can see here how my x is going up, my y is going down. Here are some examples on I guess this one is direct variation to start. And you can take a look and try to write an equation for this. And then once you have that equation written, and remember that you can use the previous slide for how you write a direct variation or an inverse variation or indirect variation equation. So try to write one for direct variation here. And you can plug in the values for z and y to find the constant of proportionality and then write a formula. So go ahead and pause the video, see what you can come up with here, and then check your answer. All right. Here you should see now that you would have direct variation y equals k times x to the a. I don't know what the constant of variation, but y varies directly with the square root of z. Then down here you can plug in what z is and what y is. You can solve for k and then plug it back in to get this equation. Next one is here's an inverse or indirect proportion or inverse variation problem. So you can try to write an equation and solve this. Pause the video now. All right, now if you've done that, this should be what you have. And then there's one more that you guys can work on. The last one is the area of a circle is directly proportional to the square of the radius. Use pi for the constant of variation. And this is what you should have. I should have paused it. Sorry, I went kind of fast there. And we can talk about any of these problems next day in class. Here are just some notes to look over and maybe start wrapping your head around and seeing what kind of summaries you can come up with. But I'll kind of go slow through this so that you can see everything that's going on here. And you might want to take notes on this in your notebook. And then the next slide is here's a graph to look at it a little closer. I don't know if that's really the right page. Oops, uh-oh. That's really the right page number that it is in the book. But this might be something you want to look at. You can color code to see when the exponents in f of x equals k times x to the n, when that exponent changes, how does that change the look of the graph? And that's if k is positive, and then over here would be if k is negative. That didn't work so well. Sorry about that. If k is negative, what do you have? And then that's that. Sorry, I'm moving the screen all over. So your classwork right now is right here, and I will check your class notes, and this come the next class.